Here's some extra practice on isotopes. Question 1 gives us 3 models, and they want to know what element is represented. And it should be hydrogen. The identity of an element is determined by its atomic number, which is the number of protons. Since all models have 1 proton, they are all hydrogen. Now there's a couple ways that you could see isotope symbols or names represented. If we wanted to go one step further, you could call this first one hydrogen -1, where the number behind the name is the mass, which really is the composition of the nucleus, the protons and the neutrons. Hydrogen 1 is the simplest atom on the periodic table. There's no neutrons, it's just a proton and an electron. And that is the most abundant form of hydrogen, because when I look at my periodic table, which is on the very back page of your textbook, the periodic table tells me that hydrogen's atomic mass is about 1.0079 blah blah blah. So it's really, really close to 1. The second one, you could call this hydrogen -2. The mass is 2. There's 1 proton and 1 neutron. And here we could call this hydrogen -3, a proton and 2 neutrons. Again, by far, hydrogen 1 is the most stable because it's most representative of the mass that appears on the periodic table. And those masses on the periodic table are weighted averages. So they take into consideration the fact that there are 3 isotopes of hydrogen, but we also take into consideration their abundance in nature. If it were just a straight average, then we would add the masses and divide by 3. The periodic table should have told us that the mass of hydrogen is 2. But that's not how we do these weighted averages. If 99.99% of all the hydrogen is hydrogen 1, then that should be most reflective of the mass on the periodic table. We can describe these as isotopes because they are atoms of the same element. They have the same number of protons, but different masses. And that comes from the fact that there are different numbers of neutrons. Question 3 had you sketch a model of carbon-12 and carbon-14. Indicate the identity of all subatomic particles. That just refers to the protons, neutrons, electrons. So whether you did like a little key and you say like what color they are, or I don't know, sometimes people like make them like different shades. Like these are going to be like I'm going to draw little lines in this one, or I'll put little polka dots in this particle. Or you just draw arrows and show the arrow for a proton, neutron, electron. Mine aren't the greatest models, I gotta admit. Carbon-12 means that it's carbon, so it has an atomic number of 6 as I look out my periodic table. So there should be 6 protons in any particle of carbon, any atom of carbon. Now, maybe you drew all the little dots and I drew my protons in purple, or you could have just drawn like 6 with a P+. That'd be like a little symbol for proton. There should be 6 electrons, and so I've got 6 negative electrons flying around what's kind of my nucleus. My nucleus got a little bit out of hand when I did the dots, but it's fine. And then the neutrons are what's different. So when the mass is 12, if there are 6 protons, then there would be 6 neutrons. So I've got 6 green neutrons in my first picture. When the mass is 14, there must be 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8. So my second picture shows 8 green neutrons. So something like that. And the most important thing is that we have the right number of protons, neutrons, electrons, and we're showing them in the right location. Excellent. Moving on. Number 3 gives us a little pie graph that represents the distribution of sodium-22 and sodium-23 in a random sample of atoms. Which color in the pie graph represents the fraction of sodium-22 isotopes in the sample? And so you find yourself kind of looking at a periodic table a lot. This number right here is on the periodic table. So you'll probably want to have a periodic table handy if you're ever answering a question about isotopes or any type of atomic structure question for that matter. So when I see on the periodic table that the weighted average mass is 22.99, well then I know that, and that's darn close to 23. Most of the atoms in the sample are sodium-23, and a small fraction are the sodium-22. The weighted average is a little bit less than 23. So the orange color is sodium-23, and the blue is sodium-22. Kind of along the same lines, in number 4, I'm supposed to sketch a pie graph showing the approximate distribution of mercury-200 and mercury-201. You may want to consult a periodic table, which again I did. I looked at the periodic table to find the weighted average mass to be about 200.59. So it's right in between 200 and 201. If it were exactly 50-50, then the periodic table would have been like a perfect average, 200.5. It's a little bit higher, so I tried to show that mercury 201 is just a little bit more abundant than mercury 200. Now, you didn't have to calculate it out to find exactly what fraction of the pie it is, but I'm just trying to show that it's approximately 50-50, but slightly more abundant toward the heavier isotope 201. If it would have been exactly 50-50 split, then the mass on the periodic table should have said exactly 200.5, a perfect average. But it's a little bit higher than that. So the higher isotope is a little bit more abundant. With number 5, they're telling me that silicone has 4 isotopes, mass 27, 28, 29, and 30. Which of the isotopes is most abundant and most stable in nature? Explain your reasoning. And so again, when I look on the periodic table to find the weighted average to be really close to 28, then I can say that mass 28 is by far the most abundant, which then also means it's the most stable of all of those isotopes. The periodic table's average mass, the weighted average mass, will always be most reflective of the most abundant isotope, or closest to the most abundant and stable isotope. Then finally, 6 and 7 have you calculating some weighted averages. And so you can use a calculator for these, obviously. Here's the gist of it. I want to take the percent abundance and multiply by the mass of that particular isotope. So in number 6, we're looking at magnesium. 78.99% of the magnesium atoms have a mass of 24 AMU. Okay, so that's a fraction of the sample. You have to use that percentage as a decimal, so make sure you move the decimal spot 2 places. So I'm going to make that like bloop, bloop, pop, 0.2899, and then I multiply by 24. And that 19.1712, that's just a mass fraction. It's a fraction of the mass that comes from that particular isotope. And then you just do the same thing with all of them. 10% of the atoms are mass 25. So I just take 0.1 times 25. And 11.01% of the atoms are mass 26. 0.1101 times 26. When you get that far, then you're going to add these fractions. Add those guys together. So I do kind of like write them down. You could store them in your calculator too. Add those little fractions together, and that would be your weighted average mass. And I can check to see if this is pretty close, because if I look at the periodic table, magnesium, like my periodic table says about 24.3. Well, depending on what data you're given, I mean, sometimes our masses are given to us a little bit more precise, and these were just rounded to the nearest whole number, but maybe it was like 24.9 something, or 20, instead of 26 it was 26.0 something. I don't know. Same thing with the percentages. Sometimes they give us more decimal spots, and that could make our answer a little more precise. But it's right there in the ballpark. It should be 24 point something. With 7, I have an element that exists in 2 isotopes. 75.77% of the atoms have a mass of 34.97. So these numbers are a little bit more precise than the first one, which just gave us like a whole number. The mass is 24. Okay, so I took that percent as a decimal, 0.7577, and multiplied by that particular mass, the 34.97, and then I get this fraction, this 26.4968, and there were way more decimal spots, but I didn't want to go too crazy. Then, what sometimes tricks people is that it says all other atoms have a mass of 36.97 AMU. They don't come out and tell you this, but that must be the other 24.23%. I mean, these percentages have to add up to 100. 100% of the isotopes in the sample. It's the same thing here, like this guy, this guy, this guy. They have to add up to 100. And so they tried to trick me. They didn't tell me it's 24.23%, but you could figure it out. And then I multiply that by the next isotope, 36.97 AMU. And then I get this other fraction of mass. Once I get those little mass fractions, you just add them. And then I get an overall mass of about 35.45-ish. And then it asks me to identify the element, which then this is the mass that would appear on the periodic table. So now I just look for the element that's got a mass closest to about 35.45-ish, and it is chlorine. So hopefully this helps a little bit. If you still have any questions on isotopes, feel free to let me know.